All right, for my calculus class, this is 1.2. And for my pre-calc class that we're starting to learn some calculus from a different textbook, this is 1.1. We are finding limits graphically and numerically, okay? So to begin with, let's talk about what the notation of a limit looks like. The question will always have limit, and underneath it, x with this little arrow, and they will give you an actual x value plugged in. This will be given, okay? They will also give you a function to plug that x into, and your job will be to find the y, okay? Limits initially is as easy as plug in an x, get out a y, okay? We talked last class and video that limits could be true whether a point exists or not. So if plugging in that x ever does not work, we have to clean it algebraically to then re-plug it in and still get out that y, okay? Now, the way you read the sentence, that arrow means the word approaches. So you read it, the limit, as x approaches, and then they'll give you a number, an actual x value, of a function, they'll give you a function, equals, and then you'll find the y value. So it's almost like finding the ordered pair, if that makes sense, okay? So you're always going to start by plugging in that x into the function. If it doesn't work, you're going to clean it using algebra and or graphing, whatever visual you need. So let's take a look at this first question. What happens if I start this limit question? It says the limit as x approaches 1 of this function. Start off by plugging it in. 1 cubed minus 1 over 1 minus 1. And what do I get? 0 over 0. Okay? Here's a quick vocabulary word you're going to learn today. You've learned when a fraction has a 0 over a number, and that equals 0. You've learned when you have a number over 0, and that is undefined. For the first time, you're starting to see 0 over 0. This is a new kind of error, and it is called an indeterminate. Indeterminate. Okay? Indeterminate simply means, hey, you can't determine the answer right now. You kind of have to manipulate it using some algebra in order to find the answer. Okay? So last class, we learned that we can manipulate that numerator because it is a difference of cubes. So we have x cubed minus, what cubed will give me 1? 1 cubed. So I can recall this x cubed minus 1 cubed, right? And the only pain in these questions is that you have to rewrite this limit until you've plugged it in, okay? And then I can expand that and say the limit as x approaches 1. Remember, we write this as first term and second term. First term squared, first and second term multiplied, and then second term squared. We follow the acronym SOAP for the signs, which means we have the same sign, opposite sign, and always positive. And now we have the luxury that these x minus 1s will cancel out. A nice little tip, I probably shouldn't tell you this, in almost every question in textbook, AP, and what you'll see in classes that are worked out nicely for you, whatever is in that denominator will most likely be one of the binomials that you can clean out in the numerator. So that should give you a head start as to what you can factor, okay? So now what I'm really doing the limit of is the limit as x approaches 1 of my leftovers. Which if I plug in a 1 into that function, what am I going to get? 3. And that is the answer of this limit. So this is how we analyze the limit numerically. If we want to analyze it graphically, well, we talked last class and video that when I cross out a binomial, it's going to give me a removable discontinuity, which is a hole. Okay? We can find the location of that hole by setting this binomial equal to 0. So I'm going to move this up a little bit. So now, graphically, I know that I have a hole when x minus 1 equals 0, which means my hole is at 1. How do I find the y location of my hole? Where do I plug that x into? If I plug it into the original, I'm going to get indeterminate again. I have to plug it into the leftovers to find out the location of my hole. And what did I find out the y value is when I plug 1 into my leftovers? 3. So I know, based off of the work up there, that my y is 3 for this hole. Okay? Now, the leftovers also give you another insight. The leftovers also tell you what the shape of this graph is going to be. What is the graph of an x squared? Some sort of a parabola. So I know that this graph is going to be some sort of a parabola with the hole at 1, 3. Okay, and because we're sketching, feel free to just draw any kind of parabola. Okay? So graphically, I could see that I got indeterminate because I had a hole, but as I approach 1 on the x, I'm going to approach 3 on the y. Okay? So now I'm going to show you briefly, and this will be the first and last time I do this because this is probably one of the longest versions to see it. But if on your calculator you put the original equation into y1, you go second graph so you can see the table. I changed my settings, which you can do with second window, to C1, which is the the number that I have the error on, and you can see it shows up there. And then I zoomed in my delta to zoom in to see a change in 0.001. So you can see that before 1, my points are 2.991, 2.994, and getting higher. And then after 1, it's 3.003 and then getting higher. So you can see through the table that from one side, it's going to get closer to 3 and also on the other. Okay? But again, we won't really use these tables much, just so you have one more visual. All right, so if you guys have ever seen Mean Girls, you see that at the end, she wins the mathalon, whatever that game was, by saying that the limit does not exist. There are 3 main ways that we will talk about that a limit does not exist. The first main one is if the limit does not approach to the same location from the left and from the right. So I just explained to my class the game when you were little that you close your eyes and you try and make your fingers touch without looking, okay? If your fingers go to a different spot, you lose. So this notation here of the plus analyzes the limit on the right side, and this notation with the little negative in the exponent spot analyzes it from the left, okay? Now, if those two from the left and the right are not equal, going to the same exact location, then the actual limit, without any positive or negative there, does not exist, okay? So the point doesn't necessarily have to exist, but the function has to exist on both sides. So one scenario that will never, ever, ever have a limit is just a dot on your graph, an ordered pair. So look at this example that we're looking at over here. This with the function, even though it has a point that does not exist, the limit can exist everywhere, okay? This dot cannot exist because it has no function coming from either side of it. Does that make sense? So let's look at the first question. What is the limit as x approaches 2 from the left side of this function? So as I approach 2 from the left side, where is it going to from the left side? What's the y value? 1. Okay? As I approach 2 from the right side, what y value is it going to? Also 1. Therefore, because from the left and from the right, they both went to 1, the full limit exists at 1. Now, I know that seems like, duh, super easy, right? Let's look at the next example, okay? I have a jump at 2. So the first question says, what is the limit as x approaches 2 from the left side? What's my y value? 3. How about the function when I approach 2 from the right side? What's my y value? 6. If from the left and the right, they do not approach the same value, you could put D and E because the limit does not exist. Okay? So when we look at these piecewise functions, remember these are pieces of functions. The functions are on the left and the restrictions are on the right, okay? So when I say x is less than 2, does that mean on 2, to the left of 2, or to the right of 2? To the left. Equals 2, on 2, and then greater than, to the right. Beautiful. Now, remember the key fact. It is very, very important to remember that anytime I have an equals and just one number, this is just an ordered pair. Okay, very important, because will I ever have a limit existing at an ordered pair? No. Now, if that ordered pair happens to land on the function, then it'll work, but we don't have to worry about analyzing that one. And we can see that happen in both questions. Okay? Let's see. So now, the first question says to analyze the limit as I approach 2 from the left. Which function am I going to look at for that? The first one, because the first one talks about approaching 2 from the left. So if I plug 2 into this function, what do I get? Good, I get 2 plus 2, which is 4. Now, the next one says to approach 2 from the right. Which one do I use if I say 2 from the right? The last one, because it says when x's are greater than 2. So what is 2 squared? Because my limit from the left and from the right equal the same, what can I say about the limit as x approaches 2 generally? It equals to 4. Make sense? All right. If you did want to draw this, you could to give yourself a visual, but you don't have to. Okay? This is a linear function that moves up to, and it's only going to exist when numbers are less than or equal to 2. Okay, so this means it shot up. So from here, whoops, my pen is sliding a little bit. Okay, let's fix that. No, you will not have to graph this, mandatory. You can if it helps you. And then it says a dot at 2, comma 4. Oops, this is also a 2. If I don't know what point that is, well, when I plugged 2 into this, I also got 4. So that's what lets you know it covers up the hole. And then x squared goes from the bottom, but it only exists after 2. If I want to know where that 2 lands, you plug the 2 in, you also get a 4. And you know that this parabola goes upward. Okay, so you can see that from the left and from the right, they are both approaching 4. Okay? Let's look at the next one. Again, you do not have to graph. As I approach 1 from the left, which of these 3 equations am I going to look at? The first one, because it says x's are smaller than, meaning to the left of 1. What is 1 squared? 1. Which function do I want to look at if it says 1 from the right? The last one, because it says numbers greater than, meaning numbers to the right. What happens if I put 1 into this equation? I get -1. So 1 times -3 is -3, plus 2 is -1. What can I say about the limit as x approaches 1? Beautiful, D and E, because the answer from the left and from the right do not match. If you want to see this graph, just for a visual, I know x squared is a parabola. If I only want it to exist after 1, okay, I know that that gives me an answer of 1. I can see that right here. And then at 1, there's an ordered pair up here for 2. And then this is a linear function going downward, okay, and has an x-intercept of 2. So the rise over run is 3 over 1. So we rise 1, 2, 3 and go over 1. And that has an open hole. And you could also see numerically that we got -1. Okay. And that shoots something like this. Okay. All right, a student just called to my attention that I made a mistake. When I drew the graph, I flip-flopped my inequality. So I drew them to the opposite direction by accident. So the parabola does go when x's are less than 1 to the left. And the linear function is when x's are greater than 1, so that's to the right. I apologize for that. Okay? So let's move on. I told you there were 3 total scenarios when the limit does not exist. 1, 2, 3. Okay? We already talked about the first one, and it's when the function does not approach the same location from the left and the right. One popular equation that we may not have memorized yet, that I do see often, is absolute value of x over x. And that graph literally shoots out to the right at +1 and out to the left at -1. Okay? It's a good one to memorize. So this is one of those key examples where the limit does not exist at 0 because there's a jump, okay? Scenario number 2 is when functions oscillate. Oscillate is a fancy word for bouncing uncontrollably, okay? I would suggest to take a moment and put sine of 1 over x into the Desmos graphing, and you'll get a graph that looks like this. And you can try and zoom in indefinitely into 0, and you're going to see that your whole screen turns the color of the function because it literally bounces so much, and it's so tight that you cannot determine what y value it's at, okay? And then the third one, I put in red their discrepancy because, I don't know if you know this, calculus was being discovered and written by 2 different mathematicians, Leibniz and Newton, and they both came up with a different answer for this question, and I'll explain to you why they both make sense. So this one says if the function increases or decreases without bounds. 1 over x squared is a graph of the 2 elbows on top that shoot up forever, right? So when you analyze it from the left, you see it shoots up to +infinity, and when it shoots up from the right, it also shoots up to +infinity. One mathematician said, hey, the limit is going to the same place from both sides, so the answer is infinity, okay? Where the other mathematician said, well, infinity is a concept. It just means they're going on forever. We don't know if they're getting to that forever at the same place, same time, therefore the limit does not exist, okay? Good news, either of the 2 answers you put in an AP test is counted correct, and they will never have both of those options on a multiple choice on an AP test, okay? So I would say get used to writing both as your answer. Know that the concept is that they both go to infinity, therefore some say it does not exist. All right, so the last thing I have to talk to you about today should feel kind of familiar from algebra, okay? Synonyms that you're going to be hearing for slope is average rate of change. Not to be confused with when they don't put the word average, because rate of change by itself means derivative, which gives you, like a derivative gives you the exact slope at one point, okay? And that's something we're going to learn in chapter 2. What we're going to go over today is average rate of change, which takes 2 ordered pairs or 2 different points on the graph and determines what the slope could be around that point, okay? So anytime you see the word average rate of change, you are just doing slope, which is the function at b minus the function at a over b minus a. So to get a little better visual about that, this would be your a point, and this would be your function at a, the y value, okay? This would be your b value, and then up here would be your function at b, okay? So what you might have been used to calling x1 and x2 and y1 and y2, so you can say y2 minus y1 over x2 minus x1 is written with a little bit of a different notation of f of b minus f of a over b minus a, but they both just mean slope, okay? And one last recap, equation of a tangent line and secant line, okay? Equation of a line is y minus y1, the slope times x minus x1. This is very old news for us, okay? The difference of a tangent line means I'm going to use the actual slope, whatever I get from this. Secant line means I'm going to use the opposite reciprocal slope. So it just means change the sign and flip the fraction. Okay, 2 very common questions in the AP test. So let's look at these last 2 examples. It says, find the average rate of change from 2 to 3. The first time I show you this example, I'm going to put one set of numbers. If they put you one set of numbers and they say from that number to that number, those are both x values. They are telling you an interval of numbers. So that is your x1 and that is your x2. Okay? So far we know that x1 is 2 and x2 is 3. So find the average rate of change. Average rate of change means that I'm going to find what? Slope, right? So I'm going to find slope from those 2 points for the equation of g of x. Then find the equation of a tangent line and a secant line. So we're doing 3 things here. Let's start off by finding the average rate of change, which means the function at 3 minus the function at 2 over 3 minus 2. Okay? So if I plug 3 into my function, 3 cubed minus 3 times x, I get, you should get 18. Good job. Now I'm going to do the same thing with 2. Plug 2 into the function, 2 cubed minus 3 times 2, I get 2 over 3 minus 2. Okay? And you should get 16 over 1, which is just 16. So 16 is the answer to my first question, which is the average, right, rate of change. Okay? Now, the next thing I'm going to do is write an equation for the tangent line. So, an equation for the tangent line means that I'm going to say y minus y1. My y value was 3. Oh, I'm kidding. It's not 3. What's my y1? 18. Let's write that out here so we have a clear view of that. When I plugged, well, let's say we call this x1. If we call 2 x1, my y1 is what I get when I plugged in my 2, which was 2. And then my y2 is what I get when I plugged in my second x. If my second x was 3, what did I get when I plugged that in? 18. Okay? Now, we have 2 options because we technically have 2 ordered pairs that we can use. Okay? We can use the 2, 2, or we can use the 3, 18. Let's write that in a new way. Let's say it was 2, 2 was 1 point, and the other point was 3, 18. Okay? You have the freedom, when they ask you these questions, to use either of the 2 points. Okay? My opinion, I like to use the one with the smaller point, the smaller numbers, so I like to use 2, 2 instead of 3, 18. So you could put y minus my y value, which is 2, equals my slope, which was 16, times x minus my x value, which was 2. And you can stop right there. The only change in a secant line is the slope. Okay? So I would write this exact same thing, but what would I do to that 16? What would I call it? Beautiful. Negative 1 over 16. Okay? And those are your 2 answers. Now, I'm going to write you the answers in case you chose to use the other ordered pair, which would still be full credit, okay? So I could have used this ordered pair here and said, this is another possible answer. And this is another possible answer. All right, for this next question, it says find the average rate of change from -1, 0 to 2, 3 for this function. So the difference between this question and the last one is the last one only gave me what looked like ordered pair, but it was my interval. Here, they did something really nice for us, and they already gave us both ordered pairs. Okay? So when you see from blank to blank, it's 2 ordered pairs. When they say from 2, 3, that means from 2 to 3. Those are only your x's. Big difference here, okay? So I can go straight to my slope being y2, which is 3, minus y1, which is 0, over x2, which is 2, minus x1, which is -1, which gives me 3 over 3. So my slope, or my average rate of change, is 1. Okay? And now, lastly, this one was a lot easier. It's always easier when they give us both ordered pairs. Go ahead and do your equation of a tangent line. And then your equation of a secant line. All right, so we have y minus, remember you are free to pick whichever of the 2 ordered pairs. Which one is easier here? All right, the smaller one. So we can put y minus y1 equals the slope, which is 1, and then x minus x1. So this cleans up to y equals 1 times anything is just 1, or excuse me, it's just itself. So I have x plus 1. Okay? And then if we would have used the other ordered pair, let's say you didn't catch to use that one, you would have written y minus 3 equals 1, which we don't have to write, and then x minus the x value. Okay? And then for the secant line, you'd have the same exact 2 equations, except my slope, I'd have to do the opposite reciprocal of 1, which is just -1. So I could say y equals, don't just put that -1 in front of that x, because there was a parenthesis. I'd have to put negative x plus 1, or you could distribute that. And then y minus 3 equals negative x minus 2.